already handing out their homework. Okay, so let's start. Okay, so let's start with question 1. So this question is actually also called the Josephus problem. So we want to prove that Jn is equal to 2k plus 1. The next survivor is 2k plus 1, where k is the non-negative integer obtained by deducting the largest possible 2 power from n. So we give you the hint, ask you to show that these 2 recursions are true, and then use these 2 recursions to prove that the closed form is true. So first we need to prove these 2 recursions is true. So when there is even number of people, we have 1, we starting from 1 and we take out 2, and 3 is alive, 4 is killed, 5 is alive, 6 is killed, so on. So we will kill all the even number person. And so we left all the odd numbers per people. And it's now become an equivalent problem with n people. And for the n people version, the people Jn is correspond to 2 times Jn minus 1. And when there are odd number of people, first we will first eliminate 2, 4, 6, and then all the people with an even number. Then 2n plus 1, then 1 is eliminated. So we will get n people remaining first. And for the people J is equivalent to a question with n people, and the people Jn in the n people version is corresponding to 2 times Jn plus 1. So now we have shown that these 2 recursions are correct. So we want to use this recursion to prove that the closed form is true. Then I would like to use induction to prove this. So for the base case, you can have the base case be 2 to the power 0 or 2 to the power 1, because we haven't, we didn't say that this game can have 1 person or not, but both cases are okay. And here, n is equal to 2, which is equal to 2 to the power 1 plus 0. So the last person remaining should be number 1. So we have first eliminate 2, then 1 is survive. So this is correct. And for inductive case, we have to consider both the odd case and even case. So, and here we use the strong induction. So we assume that for all the integer n prime less than n, the closed form is correct. So, sorry. So you have to consider n is equal to even, then use this recursion to prove that the closed form is true. And when n is odd, use this recursion to prove the closed form is true. Then we say by mathematical induction, this statement is true. So is everyone okay with this proof?
And there is one minor thing. We need to start with n equals to 1. Because if you start with n equal to 2, with the recurrence, you can only prove 2 implies 4.
Okay, so
2 implies 5.
okay, sorry, my fault.
But if you start with 1, and 1 implies 2, 1 implies 3, and then you have 2, 3, and then you but that's only just change the base case.
And for question 2, show that no matter how an n-sided polygon is triangulated, where n is larger than or greater equal to 4, at least 2 of the triangles in the triangulation have 2 sides bordering the exterior of the polygon. So I would like you also use induction here. So for the base case, we have n starting from 4, and for the base case, it's clearly no matter how we triangulate a 4-sided polygon, we will always get 2 triangles with 2 exteriors. Sorry, 2 of layer sides bounding the exterior. And when n is greater than 4, so first we are using strong induction again. And assume pk is true for all k less than n. And first we pick one of the diagonal of the n-sided polygon and draw the diagonal. So what I want to show is, we divide this polygon into 2 smaller polygons. And for each of the smaller polygon, there will be 1 triangle we want. So take this example for example. By induction hypothesis, we know that this small polygon will have 2 triangles we want bordering each side. And the triangles, the exterior the triangle corresponds to may be the first line we draw here. But we have only 1 line here, so we have at most 1 triangle which is not what we want. But we still have the other one. And for this case, it's also true. So we can find 2 triangles here and here. And for a special case, if we draw the first line we draw is something like this, then we have only 1 triangle, but we have 2 sides on the exterior. So is everyone okay with this proof? So by induction, we have the base case and inductive case. We know that for any n greater than or equal to 4, we can find these 2 triangles. 2 triangles of this kind. Okay. And for question 3, let G be a directed graph with n nodes, and V1, V2 be 2 of these nodes. So that there exists an integer p such that if there exists a V1 to V2 path whose length is greater than p, then there exists infinitely many paths from V1 to V2. And so here we have to show that there exists some p. So you can have just show us what the p is and argue that the p satisfies the property. So here I let p be the number of nodes in this graph. And so a path from V1 to V2 with whose length is greater than p, then there will be more than p nodes on this path. And because there are more than p nodes on this path, and we have only p nodes in this graph. So there must be some node V appearing twice on this place. So let me, on this place, there exists a root a subhash starting from P, then go around and going back to V again. So we can find infinitely many places in the form where we start from V1 and go to V, and going this loop for any number of times, and then go to V2. So is this question okay?
So for this question, you can just set P to be the number of nodes in the graph, or any number that is greater than the number of nodes in the graph.
Yes. And for question 4, we want to show that no matter how we color this grid, we can always find something like A, B, C, D here, where the four corners, finding the rectangle where all the four corners are the same colors. So first, we have 9 columns, and each column have 3 nodes, and each node can be colored red or white. So there are totally 2 to the power 3, which is 8 ways to color each of the column here. So by pigeonhole principle, there must be 2 of them with the same pattern. And this clearly, each column there will be 2 of them, at least 2 of them have the same color. So we can choose these 2 of the same color, and they will have we can find our desired rectangle here. So so we can say we use the pigeonhole principle twice in this example. Is everyone okay with this? Okay. And we have a no-mark follow-up. Show that if the grid is 3 times 7, then the result still holds. But if we use a 3 times 6 grid, it is possible that under some coloring, no rectangle in a grid has 4 corners colored by the same color. So for a 3 times 6 grid, you only have to find an example. My example here. So these 3 columns have 2 white dots, but there's no white rectangle here, and this is a mirrored part. The mirror part where each column have 2 red dots, but they are of a different pattern. And for 3 times 7 grid, I cannot have a very, very beautiful proof here. But here, we can divide this into 2 cases. If there are 2 columns with the same pattern, then we are done. The other case is no 2 columns have the same pattern. Then we have only 7 columns, but we have 8 ways to color each column. So there are exactly 1 of the possible pattern is missing here. And so now consider these 2 kinds of pattern. So at most 1 of them is missing. So either this exists or this exists. So without losing generality, let's assume that this one exists. Then we consider these 3 possible patterns. At most 1 of them is missing. So we can find at least 2 of them on the grid, and pairing up with, let's say we can find this one. Then pairing up with this one, so we can have these 2 and these 2 fall in a rectangle with a 4 red dots. And the same goes for if 3 white dots pattern exists. So is everyone okay with my proof? Okay. So question 5 is the Magnus direct gain. So we want you to show that when n is the power of 2, no matter what direct does, Magnus can always visit all the positions. So the idea is like this. So assuming we know how to win the game when n is equal to n divided by 2. Then what we can do is first use the strategy for n divided by 2 with all the numbers doubles. So let's say we're starting here. And the strategy for 4 is 2, 1, 2. Then we times them by 4, so we use 4, 2, 4. So when we're using 4 to 4, first we will go here. And using 2, we will go here or here. And then use 4 again, we will get the other of them. So if we number all the positions with numbers, let this be 1, 2, let me see. Let it be 0, 1, 2, 3, 4, 5, 6, 7. Then all the even numbers positions are taken out by us. Then we use 1 again. We choose 1 again. So we will go to here or here. Let's say we go to here. Then we can use the same strategy again to take out all the odd numbers positions. So to argue this method is correct, you can try to use proof by induction again. Or let's say this strategy is an algorithm, then it's actually a recursive algorithm. So this is the inductive part. Then there is only left a base case here. So the only thing I have to do is to show that the base case, let the base case be 2. Then we start from one of the position and choose 1 to go to the other. So by base case and inductive case, we show that there is a strategy to win a game for the Magnus. Is everyone okay with this strategy? Yes. And then the bonus question. So consider a game played on an infinity chessboard where each square below a certain horizon is occupied by a piece. In each move, we can jump a piece horizontally, blah, blah, blah. So this is a game. And so let's say we want to achieve to here. Then we can jump this one to here, and this one to here, and this one to here. So we want to show that although there are infinitely many check pieces in this board, there is a limit to which we can advance a piece. So first, we suppose that each square is associated with a value. Where the target square is value 1, and each square with distance n from the target square as value s to the power n, where s is equal to 0.9. And the score of the checkerboard is the total value of the squares occupied by all the pieces in the checkerboard. So we provided you 4 steps. So first we calculate what is the score initially in terms of n. So assuming the target square is n squares away, then assume it is somewhere somewhere near here. Then we have 1 piece of x to the power n, 3 of x to the power 1, 5x to the power n minus n plus 2, and 7 x to the power n plus 3, and so on. So we can sum them up to get a closed form in here. Let me see, is there any space? Not sure. Let me see. No. Also, this is just a straightforward summation, I guess. Yes, this is just a straightforward summation. And then, after a move, 2 pieces in the board will be replaced by a third one, so that there will be a change in the score. Surely when x is equal to 0.9, the score will be decreased after each move. So there are 3 cases. Let this be the target square. And the first case is one piece is jumping from a lower score place jump to a higher score place. The second case is one piece is jumping from higher score place to a lower score place. And the third case is it jumps from one square to the other square with the same score. But we have to also consider the pieces which is removed. So just checking these 3 cases, as you can see, all of them are less than 1. The score always decreases. And so, based on the result of B given an upper bound on the value of n, so first we know the target square has value 1. And the total score will decrease after each step. So which means initially the total score must be greater than 1. And to solve this equation, we can say that the largest n satisfied this equation is 49. But by tuning the value of x, we can actually show that n is less than 5. Assuming the checkerboard has a finite size. How? So first, we know that the initial total score is based on x. And when x decreases, the initial total score also decreases. So the possible distance we can go also decreases. So we want to find the minimum x such that whenever we are doing a move, the total score still decreases. So we can use this proof again. So after we solve, so we can get the minimum possible value is equal to here. And then calculate n, we can get n is actually less than 5. So is everyone can understand this question? So this is very similar to not constant. The value don't change over the time, which is invariant. Yes, the proof we use, the thing used in the proof we call invariant. So this is all of our homework over 4. So is any question regarding this homework?